Well, I hope you're comfortable and ready to watch some video about normal distributions. Popcorn is acceptable. We've looked at several distributions in the past, most notably the binomial and the Poisson, and those two have in common that they are discrete distributions. A random variable with a binomial or a Poisson only takes certain values, but the normal is a continuous distribution. Examples of continuous distribution would be things like height or weight or pretty much anything that you would measure rather than count. Discrete distributions tend to be counts. How many questions did you get right? Continuous distributions tend to be measures. How much does that person weigh? How tall is that person? So that's a distinction that has consequence for the way we calculate probabilities. For continuous random variables, we have a probability function called a probability density function. We didn't have probability density functions for discrete random variables, although we did have probability mass functions which told us how to calculate the value of the binomial or the Poisson taking on particular values. When we're looking at a new data set, we need to do several things before we really know anything about the data set. And the initials CVDOT remind us that we need to consider what is the center of our data. That's the C. How much variability is there in the data? The V stands for variability or variance. Usually we measure the variability or the variance with the standard deviation. The D stands for distribution. Is the data distributed continuously or is it discrete? Does it have a binomial or a Poisson, or in the case of a continuous? Right now we only know the normal, but we'll know a few more. Very often the answer will be it has a normal distribution. The O stands for outliers. If we have outliers, values that are unlike other data in our data set, that can throw off our estimate of the center of that data set and the variability of the data set. We also consider time, because the time that the data was collected makes a great deal of difference. If we look at the heights of American males today and a century ago, they're different data sets. The same could be said for weight. So time is an important consideration. I've recorded heights for males and females. These are American males, current time, American females, current time. And let's get a feel for the center and the variability by using Minitab and seeing what the center and the variability are within these data sets. These are randomly selected males and females. So let's go to statistics, basic statistics, display, and let's do the males and the females both. And we'll pick statistics that we want. Let's get the mean. I don't need the standard error right now, but we do need the standard deviation. I don't think we have a need right now for the quartiles, so we'll unclick those. Let's keep the minimum and the maximum, and let's look at the total number of data pieces we have in each of those data sets. And we'll say OK, and OK again, and here's our results. And you see that I've got 500 males and 500 females in the data set, so that's a pretty good sized data set. The males tend to be taller. The mean is 69.5 versus 63.8 for females. Standard deviation, the females show more variability. We can graph the heights. We could do both, but let's just do the males. And so let's put a title on our graph, male heights. And by looking at the histogram, we can get a feel for whether the data appears to be normal or not. So we'll say OK, and let's say OK again. And here's a picture of the histogram. And notice that the mean was about 69, and that's the high point there of the histogram. We've got a lot of tall columns clustered around about 69. The distribution appears to be roughly symmetrical, left and right. It falls off to both the left and the right at about the same pace. So that would be a histogram that would look pretty much like a normal distribution. I have confidence that this height data for males is pretty much normal. As a final test, we could look at the test of normality that's built into Minitab. So why don't we do that? We'll get the histogram out of the way. We'll go to Statistics, Basic, and down toward the bottom is Normality Test. And our data is in column C1, Male Heights. And we'll select the Anderson-Darling test, which is selected by default. And we'll say OK. And here's the result of the Anderson-Darling test. And the way to read the graphic is realize that the red dots represent data in our data set. So every red dot was the height of some male. And the blue line is where the red dots would lie if the data were perfectly normal. Well, of course, it's not perfectly normal, but you can look at how close the red dots are to the blue line and see that it's pretty darn normal. So we wouldn't have any problem calling this a normally distributed data set. Height is a normally distributed data set. So that's enough for this first video, and we'll be right back with the second video on distributions.